Welcome back. In our last class, we found out that light can form an interference pattern when we have two slits that the light travels through. This happens because of the wave nature of light, and that there is different path lengths between the two slits. The light travels a different distance. So this produces an interference pattern because when the path length difference corresponds to the wavelength of the wave, or a multiple of that wavelength, then we get constructive interference. So the light is in sync with itself. So if our light has a wavelength of 400 nanometers and the path length difference is 0, 400, 800, 1200 nanometers, then it's going to be constructive interference and you're going to have a bright spot. If the distance corresponds to 1/2 the wavelength, then the waves from the two sources become out of sync, and so the difference in path length is 200, 600, 1000 nanometers for 400 nanometer light. Then the interference will be destructive and you'll have a dark fringe. So the same thing can happen for a single slit. In this case, it again happens because of the wave nature of light, but now light from one portion of the slit interferes with light coming from a different part of the slit. So we look at our single slit here, and we see that the interference will depend on the difference in the path length between the light leaving the edge of the slit and the light leaving the center of the slit. The reason we pick the center is that if the center will interfere with the edge, but also then what happens is if we look at light that's just a touch below the edge, then that will interfere with light that is just below the center. And the light coming out even below that, more below that, then it will interfere with light that's even more below the center, and so on. So the result is that you get interference from all sort of parts of your all of the light going through that slit. So to find the difference in the path length, we do what we did with the two-slit problem, but now we're comparing the center and the top edge of our aperture here. This makes a new triangle, with the hypotenuse now being 1/2 the distance of the aperture, or 1/2 the diameter of the aperture, and so the wavelength difference will be d, the diameter of the slit, divided by 2 times the sine of theta. So the first dark fringe will occur when the path length is 1/2 lambda. So if we set d over 2 times sine theta equal to 1/2 lambda, then d sine theta is equal to lambda. So that's when the first fringe will form. The second dark fringe will occur when the path length is 2 times lambda, so then d sine theta is equal to 2 lambda. From this, we hopefully see that the d sine theta is equal to m lambda, where m is any integer except for 0, and m equals to 1 corresponds to the first dark fringe, where destructive interference occurs. Notice, if m is equal to 0, then there's a bright spot, because the path length will be the same for the light on each edge, for example. Also, notice that this makes a pretty different image than the two-slit pattern. This pattern has one very bright peak in the middle, and then a dark fringe, and then the light interference pattern goes through lighter and darker fringes, but those light fringes are much weaker than the central fringe here. So what do we see when light is shown through a small circular aperture, or really any circular source of light? So an aperture is some hole or opening that light passes through, and that's all that I really mean by an aperture. So the light spreads out as it leaves this aperture, and it produces an interference pattern. For a circular source of light, the formula changes a bit. The first dark fringe now comes at d sine theta being equal to 1.22 times lambda. This means that if we have a source of light, this is how much spread that light will have. This also means that if we decrease the wavelength of light, then the size of this central fringe will decrease in size. So in fact, if we go to other kinds of waves, like electron waves, then we can drastically decrease the spread due to the smaller wavelength. So this is why electron microscopes can form images with greater magnification than a light microscope. On the other hand, as the diameter of the aperture decreases, the size of the central fringe increases. This is a little surprising, but the smaller the aperture, the smaller the difference in path length of the light leaving the aperture. That means the light needs to travel at a greater angle in order to get the difference in path length and for a destructive interference to then occur. And that means that the larger the wavelength, the larger the fringe, and the larger the aperture, the smaller the fringe. So one application of this is that the resolution, the ability to distinguish between two objects, is fundamentally limited by the wave nature of light. So if two objects are so close that their destructive interference-based dark fringes overlap with each other too much, then no matter how good your lens is, you will never be able to distinguish the two. So you can see here that there are two sources of light. On the left, you can't really be sure that there are actually two sources. It could be just one slightly oblong single source. On the right, we can just barely confirm that it is indeed two separate objects. That means that the angle is just more than twice 1.22 divided by the diameter of the aperture. That is the angle you'll have to have, so you'll have to do some trigonometry to find the distance. So if this difference in angle is 1.22 lambda over d, then the two center peaks will overlap, but you can probably tell that there are two separate sources. So this idea is called the Rayleigh criterion, which relates the size of the central spot to the ultimate limit at which two objects can be distinguished. So the Rayleigh criterion is that if the dark fringe of one passes through the center of the bright spot for the other, then that is considered to be the closest two things can be where you can still tell them apart. So to meet Raleigh's criteria, the sine theta, where theta is the angle between the two sources of light from the position of the observer, is equal to 1.22 lambda over d. Then Raleigh's criteria is at its limit. If the angle is larger, then the two objects can be resolved. If it's smaller, then they cannot be resolved. So we have a problem to do here. We have two headlights on a car are separated by 1.1 meters. Assuming that the light is 460 nanometers, and assuming that the pupil diameter is 5 millimeters and the index of refraction of the eye is 1.36, then what is the furthest distance that an eye can distinguish the two headlights? Well, the sine theta, we can just call that theta in radians, which is 1.1 meters over the length. So next, that is set equal to 1.22 times lambda over d, where d is the diameter of the aperture. So the general form is y over L is equal to lambda over d, and so the length, the distance to the car, is equal to 1.1 meters times 0.005 meters divided by 1.22 and divided by 460 times 10 to the minus 9 meters. Right, so that's our lambda. That gives us a distance of 9,800 meters, assuming that the eye is a piece of perfect optical equipment. Notice that the index of refraction was not relevant here. That's just a confuser. It's the path of the light through air that matters on whether you can resolve it or not. So to put this in perspective, let's compare the angular resolution required for 20/20 vision with the limit of what is possible with visible light. For 20/20 vision, you are reading lettering that is 8.8 millimeters high, that is 6 meters away. To read this, you need to be able to resolve about 5 times smaller than the letter, so let's call it about 1.75 millimeters. So the angle theta, using the small angle theorem, tells us that the distance apart divided by the length gives us that angle in radians, so 0.00175 meters divided by 6 meters gives us about 2.9 e to the minus 4 radians. The Rayleigh criterion, so the best possible resolution for visible light, is 1.22 times 500 times 10 to the minus 9 divided by the diameter, which is 0.005 meters, and that gives us an angle of 1.22 times 10 to the minus 4 radians. So that means that the Rayleigh criterion, it has about 1/2 the angle for the best possible value for the human eye. That means the human eye has about 2 times less than the physical limits of resolution for visible light. Pretty impressive. Okay, so you guys have a few questions to do, and next we're going to look at thin film interference.